We will now look at the properties of the Mercator chart, under the heading set out in the introduction to this lesson. A Mercator chart with a cylinder touching at the equator is called a normal or a direct Mercator. This is to distinguish it from the transverse and oblique Mercator projections, where the cylinder is either sideways on or at some oblique angle. We will discuss these in a later lesson. The first property to be examined is scale. We know that the reduced Earth touches the cylinder at the equator, so that at that point the scale must be correct. However, as we move away from the equator, the same distance on the chart represents a smaller distance on the Earth. The scale is expanding. The denominator is reducing. The relationship between scale at the equator and at any other latitude is given by the equation scale at any latitude equals scale at the equator times secant of the latitude. Let's show by a practical example how this equation works. Suppose the scale at the equator to be 1 to 1 million. Let's find out what the scale would be at 8 degrees north or south. The equation now becomes scale at 8 degrees north equals 1 to 1 million times secant 8 degrees. However, we don't have a secant function on our calculators. More importantly, representative fractions are always expressed with 1 as the numerator. So we write the secant as 1 over cos, which makes the equation scale at 8 degrees north equals 1 to 1 million times 1 over cos 8 degrees. Cos 8 degrees is 0.9903, which we can take as near enough to 0.99. So the scale at 8 north is 1 over 990,000. We use this as an example of how to calculate scale expansion using the Mercator scale change equation. However, 8 degrees latitude also has a particular significance. Our calculation has shown that between 8 degrees north and south, scale is within 1% of that at the equator. We regard a scale distortion of 1% or less as being constant scale, for most practical purposes. This means that between 8 degrees north and south, Mercator chart distances can be measured with a ruler, and the error will be generally acceptable. So, to summarize, Mercator scale is correct at the equator. Elsewhere, it expands as the secant of the latitude. It is within 1% of the equator scale between latitudes of 8 degrees north and 8 degrees south. And incidentally, it is also within 0.5% between 6 degrees north and south. It is perfectly possible to use a Mercator chart outside these latitudes, but distances cannot be directly measured with a ruler. Here is a Mercator chart which covers latitudes from 51 to 55 north. If we open a pair of compasses to the distance between latitudes 52 and 53 north, it will represent 60 nautical miles between these latitudes. If we leave the pair of compasses the same distance apart, but move it to between 53 and 54 north, it now indicates 59 nautical miles. And between 54 and 55 north, the same distance now represents 58 nautical miles. The chart length is the same, but the scale is changing. We must take account of this if we want to measure distances. Suppose we have this track distance from A to B. We have to measure using the local scale. We open our compasses to a convenient length. On this particular chart, this corresponds to around 60 nautical miles. For charts with different scales, it will represent a different distance. We pick a latitude at or near the halfway point. We then find the latitudes 30 miles either side of it, to balance out the scale error, and measure precisely 60 nautical miles between these latitudes. We use our compasses to arc off a distance of 60 nautical miles to go to the destination. We now pick the mid-latitude for the next segment of the route. Note that, because it is nearer the equator, we have to close the compasses up a little. Again, we use our compasses to arc off a distance of 60 nautical miles at the new local scale. This now gives us 120 nautical miles to go to the destination. And finally, we measure off the last remaining distance, also using its local latitude. In this case, the total distance comes to 158 nautical miles. You can see that this is not a particularly difficult procedure, but it does need a large flat surface, such as a desk or table, which are no longer available on modern aircraft. It is not suitable for a handheld plotting board. This is why, these days, Mercator charts tend not to be used outside equatorial latitudes. These are the points that you should remember about Mercator scale. The next chart property to consider is orthomorphism. Mercator's projection is orthomorphic. Meridians and parallels cross at right angles. And Mercator designed it such that the scale expands equally in all directions. So the Mercator chart is orthomorphic, but non-perspective. A graticule is simply the term for the network of latitude and longitude lines on the chart. Meridians are equally spaced straight parallel lines. Parallels are straight parallel lines with the space between them increasing as the secant of the latitude. How are shapes affected by the projection? In equatorial regions, shapes are reasonably accurate. However, at higher latitudes, land masses appear too wide for their height, compared with the same land mass on the globe. Compare the shape of the North American continent on a Mercator with its shape on the globe. The continent appears too wide. The east-west distance from Labrador to western Alaska seems too great, compared to the north-south distance from northern Alaska to the Gulf of Mexico. Also, look at Greenland on the Mercator projection. It looks about the same size as the whole of the South American continent. But on a globe, you can see that it is not. Greenland is actually about the same size as this shaded area in the Horn of Africa, Ethiopia and Somalia. This size and shape distortion is caused by scale expansion. This distance represents 3,000 nautical miles at the equator. At 60 miles to a degree, that is 50 degrees of change of longitude at the equator. But at 60 north, 3,000 miles of departure is now equivalent to 100 degrees of change of longitude. The distance on the Earth is the same, but it is twice as wide on the map, which is why the continent shape seems wider compared with the globe. These distortions become apparent only on a global scale. When comparing continents, they give a false idea. However, they are insignificant over small distances, and therefore have no effect on a pilot's ability to map read. You would not be comparing Greenland and South America at the same time if map reading. You would either be in Greenland, in which case the shapes would be in the correct proportion to each other locally, or you would be in South America, where the shapes would also be locally in proportion to each other. but they can give a false impression of the most direct routing, especially at high latitudes. We have already covered the concept of Earth convergence, or convergency, in a previous lesson. It is the angle of inclination of meridians on the Earth, or the change in direction of a great circle on the Earth. Chart convergence is the angle of inclination of meridians on the chart, or the change in direction of a straight line on the chart. On the Mercator chart, as all meridians are parallel, their angle of inclination to each other is 0. The change in direction of a straight line is also 0. It will always cut all meridians at the same angle. That is why Mercator produced the chart in the first place, so that a straight line on the chart gives a single track angle. Earth convergency is also 0 at the equator, but nowhere else. Therefore, Mercator chart convergence is correct at the equator, but nowhere else. Mercator convergence is constant all over the chart. It is always 0. We already know how rhumb lines appear. Because the meridians are parallel lines, a straight line track on the chart will cut all meridians at the same angle. A straight line track on a Mercator chart is a rhumb line. How will great circles be portrayed on this chart? How will great circles be portrayed on this chart? On the Earth, great circles are the most direct track. Therefore, they will always lie nearer the pole than the equivalent rhumb line route. So, if the rhumb line is a straight line, the great circle must be a curve concave to the equator. The equivalent situation in the southern hemisphere will be like this. And where a rhumb line and a great circle cross the equator, the crossing point is the same, and the great circle is concave to the equator in both hemispheres. Let us look at this route from London to Los Angeles, Los Angeles to Auckland, New Zealand, Auckland to Singapore, and from Singapore back to London again. Note that the route from London to Los Angeles is all in the northern hemisphere. LA to Auckland crosses the equator. Auckland to Singapore is all in the southern hemisphere. And Singapore back to London is all in the northern hemisphere again. This is on a Mercator chart, so the straight lines joining these points are all rhumb lines. However, always bear in mind that they are not the shortest route. It is a distortion of the chart. Now, remembering where the equator is, try to visualize where you think the corresponding great circle routes will appear. It should look like this. Did you get it right? It may seem counterintuitive, but the curved lines actually represent the shortest route. Most people underestimate the amount of curvature on the great circles. But we can work it out. Let's take the London to Los Angeles leg. The initial angle between the great circle and the rhumb line is, of course, conversion angle. Conversion angle is half change of longitude times sine mean latitude. London is on the Greenwich meridian. Los Angeles's longitude is about 120 west. So half of 120 degrees is 60. London's latitude is about 52 north, whereas LA is about 34 north. So the mean latitude is about 45 north. Sine 45 is about 0.7. Multiplying out, the conversion angle should be about 42 degrees. Now have a look at the diagram again, and you'll see that it's about right. Try the same exercise with the other conversion angles. Notice that you have to split a track crossing the equator into two curves, one in the northern hemisphere and the other in the south. But the arithmetic still works for each section. So now let's summarize these properties. We'll list them and go through them more briefly this time. Scale. Scale is correct at the equator. Elsewhere, it expands as the secant of the latitude. It is within 1% of the scale at the equator, up to 8 degrees north or south of the equator, and within 0.5% up to 6 degrees from the equator. The chart is orthomorphic. All charts used for navigation must be. The graticule. Meridians are straight parallel lines, evenly spaced. Parallels are straight parallel lines with the space between them increasing as the secant of the latitude. Shapes. Shapes are reasonably correct over small areas, but there is distortion over large areas, especially at high latitudes. Chart convergence. The chart convergence is 0 everywhere. It is correct at the equator and constant across the chart. Rhumb lines. Rhumb lines are straight lines. Great circles. The equator and meridians are straight lines because they are also rhumb lines. All other great circles are curves, with a track nearer the pole, or concave to the equator. That concludes the lesson on basic Mercator properties. In the next lesson, we will examine the calculation of Mercator scale change in more detail.